Hello everyone, this is Mrs. Gabriel, and I am bringing to you part 2 of the Unit 8 presentation on aquatic and terrestrial pollution for your APES exam preparation. Our first topic will be on eutrophication. Okay, we're looking at two pictures here of algae, and both of them are an overabundance of algae. In this one, you can see all the little green algae floating around in the stream. It's already creating a little bit of a problem for anything underneath it, such as blocking sunlight, and it's capturing more sunlight, so it's going to grow very well. It can get to the point of toxic algae where animals, it's just too much. Animals in the aquatic food chain are going to die, and humans can even get sick from certain types of algae. So toxic algae is one that we can get sick from. And most algae blooms, they can happen anywhere naturally, and algae blooms can be controlled by the ecosystem they're in. However, humans can input excessive amounts of nutrients, and that's going to cause algae blooms to the point of eutrophication and even a dead zone. Now, if you look at the map over here, we see the Chesapeake Bay again, and we're looking at oxygen levels. And dissolved oxygen levels are related to algae blooms, which we'll talk about more, and I've already introduced you to. But red means we're in hypoxic waterways, which is without oxygen. It's just not enough for any organism to survive. Now, what are the sources that are causing all these nutrient inputs that lead to eutrophication? They're in the bullets right over here. So cultural eutrophication is anthropogenically caused. Cultural means by humans, okay? So it's not natural. So cultural eutrophication is where the runoff carries these excess nutrients. And the runoff can come from rain, snow that is melted, or irrigation from farmers. It goes into streams, ponds, lakes. Ooh, I didn't spell ponds, so I'm missing an end. But it comes from excess of fertilizer, sewage from wastewater treatment, nitrogen from animal manure, and phosphates from detergents. So eutrophication occurs when a body of water is enriched in nutrients. Now, one of the essential knowledge statements that you need to be very comfortable with is comparing eutrophic waterways to oligotrophic waterways. So let's start by looking at the two pictures over here. Look at an oligotrophic lake and a eutrophic lake. So oligotrophic is usually a younger lake. It hasn't been around as long. And notice that we have more like rocky sides. It's much more clear, doesn't have as much plant growth. Eutrophic lakes are older lakes. So here we go looking at the eutrophic, and you notice that it's our older lake, which would make sense because there's a lot more sediment that has filled in the lake, which makes it more shallow. And if it's more shallow and we have all these plants that have become more abundant over time, we're going to have a lot more productivity in this lake. So if you look at the chart over here, we also have some other differences. Oligotrophic is going to have lower nutrient levels. It's going to have stable plant and algae populations, and it's going to have a lot of dissolved oxygen, and also this deep zone that's very, very cold water. And that leads to a little mixing in here. All that cold water, remember, colder temperatures are going to hold more dissolved oxygen. And the eutrophic lake, which is the older lake, it's the one that's filled in with sediments, it's been there a much longer time, they tend to have higher nutrient levels, higher plant and algae populations, and lower amounts of dissolved oxygen. So remember that. Now back to nutrients. Remember that overabundance or excessive amount of nutrients is going to help those plants and algae and cyanobacteria, which is like a type of algae, grow rapidly. And then know the difference between your eutrophic and oligotrophic waterways. Remember its relationship with dissolved oxygen. Okay, so we have our stable aquatic system where our dissolved oxygen is high. You can see it on our dissolved oxygen meter right here. And you can see our plants and our fish and everything else that's in the system here, right? And then we go to our eutrophic. Remember, that can be natural, but it can also be cultural. So eutrophic systems are the ones where we've been exposed, the organisms living in here have been exposed to excess amounts of nutrients. So let's call this one cultural. So excess amounts of fertilizer are now up in the stormwater runoff, just rain, okay, rain runoff, and they came into the aquatic system, and the algae, because they're plants, are going to go crazy with this input of extra nitrogen and phosphates, and they're going to reproduce, and there's going to become an algae bloom. So the algae that was kept in check over here in the stable aquatic system is now going to overgrow. And our dissolved oxygen levels are still high here, but as the algae die, they're going to sink to the bottom, and there's going to be all these microbes that are going to decompose the dying and dead algae. And those organisms, those microorganisms, are also taking all the oxygen out of the water. So there's less oxygen available. So that oxygen is rapidly consumed. And notice on our dissolved oxygen level meter that it's very, very low. Once those microbes, there becomes an overabundance of those microbes, their population grows very, very rapidly, and they take the oxygen out of the water. This is the point where we call it a hypoxic aquatic system. It's hypoxic, which is low, low, low oxygen levels. Now, when we have that low oxygen level, then we're going to get a fish die-off. And when we have large amounts of this, it's called a dead zone. And remember that oxygen sag curve. We talked about that with dissolved oxygen levels, and that's very, very related to hypoxia, which is that overabundance of nutrients now causing this to happen. So before I show you the next few slides, let's just review a little geography, just in case you have forgotten some of your basic rivers and states. So follow where my pointer is in the Texas area. And we're in the Gulf of Mexico where my pointer is right now. This is the Gulf of Mexico. This is the mouth of the Mississippi River entering into the Gulf of Mexico. Followed that river all the way up, and as I've reviewed with you before, everything that runs into this river brings whatever pollutants are in here, or even all the way over here in Colorado. They run downhill into this Mississippi River. So let's go all the way to the top of the Mississippi River. So the Mississippi River flows towards the Gulf of Mexico. Everything from the Illinois and Missouri River and everything they've picked up along the way accumulates, concentrates. Everything from all the way over here, West Virginia, Ohio, Kentucky, and the Ohio River, they all carry all their extra nutrients into the Mississippi River, which then accumulates higher and higher concentrations of nutrients, and then it empties out into the Gulf. Here you'll see the Mississippi River and its entire watershed, all runoff from all these areas within this white boundary, end up in the Mississippi River and then end up in the Gulf of Mexico. And then these are watersheds for each of those tributaries that go into the Mississippi River. So here's Texas over here, Louisiana, Mississippi. The Mississippi River empties right into the Gulf of Mexico. And the red, as we've discussed before, means this is probably a hypoxic zone. This is our dead zone. Dead zone. Remember this. Dead zone. Intense eutrophication leading to hypoxia. So remember, the dead zone in the Gulf of Mexico starts with the Mississippi River water that carries all that extra set of nutrients in, that nitrogen-rich material, and it really comes from fertilizer and runoff and even sewage, empties into the Gulf, and then all the smaller organisms that are plankton, like phytoplankton, end up doing extremely well, and the algae does extremely well, and it grows and grows, and then we have an overabundance of it, and it dies. And when it dies, microscopic organisms feed on everything that died, and then they use up all the oxygen. And then you can read all the details of how this works on your own. So there's a 3-minute video on the eutrophication process, and what I like about the video, it's animated and live feed to show you what it really looks like when you get to the dead zone, where eventually it becomes hypoxic, no oxygen, or such a small amount of oxygen, dissolved oxygen, where the fish die. Okay, just to remember, eutrophication is where we get the excess nutrients from fertilizers, the algae die, then the oxygen-consuming microbes digest them, and that reduces the dissolved oxygen, and then other fish and organisms die, and that's hypoxic waterways, which leads to a dead zone. And here's your multiple choice practice. I recommend that you pause this part of the video and you review each of these essential knowledge statements, repeat them to yourself, and then tell yourself or whoever feels like listening to you what else you know about each of those topics. Practice writing about them or talking about them. Okay, now we're going to move on to a nice short little topic, 8.6, which is on thermal pollution. Besides the obvious one that we've discussed before, where a power plant might release its warm water back into whatever body of water is nearby or discharge it back into the water, that water is then heated. Besides that one, which we've talked about before, there are other sources that will discharge more indirectly warm water or warmer water back into the bigger body of water. And those other sources that could bring warmer water with them include soil erosion, because it can take in the sunlight more and it can heat up the water from all the particles in the water. So they might have a different albedo or a lower albedo and absorb more of that sunlight into the water. Deforestation, which means we have less shade, which means that the water is going to be heated directly from the sun. And then discharge from wastewater treatment plants, which we'll talk about later. And then urban runoff. So all the runoff from the roads. And I'll show you some pictures of that to kind of remind you. Now, thermal pollution occurs when heat is released into the water. We know that part. That's the easy part. But why it's an environmental science is because it produces negative effects to the organisms in that ecosystem. So here's a source, like if we think about our streets and it's a hot summer day and you see the cars driving here, think about how hot that road can get. And then we have a rain event, and the rain gets superheated while it's also cooling. It's getting superheated, this water, from the hot street. And then it goes into the storm drain, and then eventually that storm drain gets emptied out into a larger body of water. And that's all warm water that's coming with it. That's urban runoff. Urban runoff. And it's also carrying all these other pollutants with it from the roadway. But this can be much warmer than this water. And remember, that warmer water is going to produce negative effects to the organisms in the ecosystem. So some of those negative effects that occur to the organisms in the ecosystem could be their range of tolerance. And that range of tolerance could be narrow or it could be wide, but still there's a range of tolerance for the organisms. And remember, it changes their fitness and the stress levels. And once organisms get stressed, their eggs, their larvae, the babies, even their ability to fertilize changes. Under stress, they're no longer able to even reproduce. We can get more die-offs, and more die-offs occur because the dissolved oxygen levels are lower, which I'm going to prove to you in a second. And feeding, breeding, and migration behaviors can be altered because of that warm, intolerant condition. So, dissolved oxygen. As I told you several times this year, and explained to you several times this year, if the water is colder, it can hold more dissolved oxygen. Well, here's evidence of that. So we're going to follow two lines on here. The blue line is for water temperature, and the red line is for dissolved oxygen. And we're looking at months of the year. So following from January all the way to January of the next year to January of the next year. So you know that we're in July here, which think about what your July is when we look at temperatures. Okay, so the water temperature is going to be warmer in July, cooler in January, right? So if we follow our cooler temperature waters, notice that the dissolved oxygen levels are much higher. As our water temperature gets much warmer, our dissolved oxygen levels get lower. So how do we know this is not just some strange anomaly that could be caused by something else? We have followed this type of data season after season after season. And we've noticed the same patterns. Dissolved oxygen will be higher when the temperature is lower. And critters need that dissolved oxygen. So thermal pollution is going to make the temperatures much warmer, which is going to make the dissolved oxygen levels too low. So those variations in water temperature affect the concentration of dissolved oxygen because warm water does not contain as much oxygen as cold water. So here's another way of looking at the data that supports the statement that I've been teaching you all year about this temperature and dissolved oxygen relationship. So here we're looking at just a chart instead of a graph, and the chart shows you very low temperatures going to very, very high temperatures. And the amount of oxygen that is in the water in milligrams per liter, it's dissolved in the water, is much higher with the low temperature. And as the temperature increases and increases and increases, and there's a big jump right here, we notice that the solubility in this time milligrams per liter decreases and decreases and decreases. Okay, so we've seen this picture before. So this is a power plant, and as you already know, power plants release warm water or discharge warm water because they're using it for cooling, right? And or they're using it as it gets heated through steam and they release it back into the water. And manatees are the animals that are all in this water because it's wintertime and they're looking for a warm place to stay because they're mammals and they want that warm water. So let's look at our little manatees up close. Aren't they cute? Now these are Florida manatees. Like I said, they're mammals. So they like to stay warmer, and manatees have always been interested in the habitat of seagrass. And they also, because they like to still stay warm in their water, but they like being in water where there's a lot of fish, so the dissolved oxygen levels need to be high enough for them to catch what they need. The manatees need to find hot springs, and they're just like little cracks or little seeps, little holes in the shallower and some of the deeper, but they hang out near the shallow ends of the ocean, and they find where that hot spring is, and they warm from it. So in 2021, manatees experienced starvation as the weather turned colder, and manatees gathered around these unnatural warm water sources like the power plants, and the food was scarce. So it's a death trap because it's a food desert, and that's because of thermal pollution and also because of nutrient pollution. There was no food there. The mammals are just wanting to get warm, and their natural hot springs have disappeared due to agricultural sediment runoff and development just clogging their springs. So they're just looking for warm water anywhere. But it's a food desert. And here's another description of that from AP Classroom, which I will not read to you, but I do like the last question at the bottom. So how do you think it is that lower dissolved oxygen levels by the power plant where it's warmer water because of thermal pollution, how do you think that dissolved oxygen level itself is not a problem for manatees? Never mind the fact that, they can't get their fish because it's a dead zone for fish. But why is it not a dead zone for them? Well, it's because they're mammals and they come up for air. So they're not actually breathing the water dissolved oxygen in the way that fish use the dissolved oxygen for living. They actually come up to the surface and they breathe air to survive. Okay, I'm not going to read you all the facts here because I've talked about them, but I do recommend that you read this multiple choice question and then just remember it. Once again, these are your essential knowledge points for this unit or this topic. Okay, this topic's going to be a little more tricky. We're talking about persistent organic pollutants here. So a little background on our POPs, or persistent organic pollutants. They are banned for use in the United States. Banned for use in the United States. But the reason they're still a problem, even though they've been banned, is because they don't easily break down in the environment because they're synthetic and they're carbon-based molecules. And some examples that you've heard of before this year are DDT and PCBs. So if you look real closely at this insect spray that's no longer manufactured or sold in the United States, it says DDT insect spray. And here is a picture of how widely used it used to be in the 60s and 70s, where there was an insecticide truck that would go around into neighborhoods and just spray insecticide that included DDTs in it. And DDT is just a molecule, a synthetic molecule that's a persistent organic pollutant. And here's DDT if you're interested in looking at its molecular makeup. So it's a persistent organic pollutant, or a POP. Persistent, it lasts for a long time. Organic, there it is. Synthetic, and it's nonpolar, which you can see from here. Now, DDT itself, we know it's an insecticide, and that's what it stands for. And it's a colorless crystal, and like I said, it's banned in the US. Oh, and we sprayed that insecticide, just to make clear, because we were trying to kill mosquitoes. And mosquitoes can carry malaria, so it is used in other countries where malaria is a problem, and we know that DDT is successful in killing those mosquitoes. So remember, POPs, or persistent organic pollutants, are persistent organic synthetic nonpolar. DDT is an example of that. So Rachel Carson is an environmentalist who she wrote a book in the 70s about, she was one of the first ones to bring persistent organic pollutants to the news and the media, and she started the awareness of us becoming very aware of how dangerous DDT is for the environment and ecosystems and human health. So Rachel Carson, very important name. And remember, it is still used in other countries. And other POPs include PCB, which is an industrial chemical, which is also banned. So some of the long-term effects of persistent organic pollutants is they can get into our water and our soil. And then the persistent part, they last for a long time. They don't break down easily. They're fat soluble, and they'll accumulate over time. So they last for a long time, and they accumulate over time. And they can be carried in the water, they can last in the soil, they can even be carried in the wind, so they have a global impact. And here is an example of PCB. Now remember that I told you that they're fat soluble, so they're not going to break down, they're just going to accumulate into the fatty tissue of organisms. So where can we still find some of these persistent organic pollutants? Well, they're still found in a lot of our electrical parts, okay, like capacitors, transformers, and a lot of these old cable insulators, they still have especially PCBs in them, not DDTs, the PCBs. And then construction, any of those softer plastics, they use PCBs in order to make the plastic softer. Any kind of glaze that they've put on windows includes PCBs. And then any kind of sealant they put on floors, any kind of caulk or grout, if it doesn't say PCB free, it probably is not PCB free. We can also find PCBs in paints. If you do not buy a paint that is PCB free, then assume that it has PCBs in it. And then I'm not going to read all these other things, but pesticides is a really big one too. So persistent organic pollutants can travel over long distances in wind and water before they get deposited somewhere. They don't have to be created somewhere locally and only stay local. And then as they travel, remember, they're not going to break down. So PCBs, unlike DDT, that's like a yellow liquid and an industrial fluid. And remember, just because it's banned doesn't mean we can't find it in a lot of things. But here is what you need to worry about with humans and our exposure to PCBs.
These are all the impacts of PCBs on human health. So the PCBs are still out there from us using them in all the materials that I just listed that are still around, and PCBs weren't banned that long ago. So we might have old paint in our houses, we might have old sealants, and by old I mean just 10 years old. We might have caulk that's 10 years old. So we might have old soft plastics that have PCBs in them. And if you are exposed to these PCBs, you're ingesting them, it's going to stay in your fatty tissue. And if it's in your fatty tissue, you can get liver disorders, failure to reproduce, different types of cancers, especially liver cancers. You can get hormone issues. You can get immune system suppression and other carcinogenic effects. And remember how I told you that they can travel long distances. So this is an example of a map that reminds you of our westerlies and our trade winds. So our westerlies are the blue. So if we have persistent organic pollutants that have been applied somewhere over here, they travel and they don't break down while they're traveling. They can travel the globe. They can travel the globe. And even our trade winds can carry these around and deposit them anywhere. And then you have it in your yard, you grow a garden out there, and it gets taken up by the plants that you're growing, you're ingesting it, and then you have the human health issues. Here's our pops traveling in the ocean. Take a look at the currents to remind you of how they travel. And wind. So, as I told you, persistent organic pollutants have long-term effects, and they're so bad, and we know that they're that bad. They're so bad that there was an actual international convention to discuss the human health and environmental concerns with the manufacturing and usage of persistent organic pollutants. And it was called the Stockholm Convention. So they're on it. And because of this special convention, there was a global treaty which aimed for countries to stop manufacturing, selling, using, and distributing any kind of POPs. Other monitoring agencies are the EPA, and under the Clean Water Act, they are also monitoring it in order to make sure that we are removing POPs from water by using mitigation strategies if it's somehow getting in there. It's also monitored under the Safe Drinking Water Act to make sure that we are not drinking water that is contaminated with POPs. It's also monitored under RCRA, the Resource Conservation and Recovery Act, and CERCLA, the Comprehensive Environmental Response Compensation and Liability Act. So it's a big deal that we get persistent organic pollutants out of our air, our water, and our soils. Here are the essential knowledge statements for topic 8.7, persistent organic pollutants. Make sure that you know them and how they're worded. This is our last topic for this presentation. It's 8.8, bioaccumulation and biomagnification. Good news, we've already been touching on this several times this year, so I'm able to fly through it faster. Okay, so substances that can bioaccumulate are DDT, methylmercury, and PCBs. And something that they all have in common is that they don't break down. So bioaccumulation is the selective absorption and concentration of elements or compounds, and these are your compounds, guys, by cells in living organisms, and most commonly fat-soluble compounds. These are it, guys. Now, biomagnification, if you look at these pictures over here, I'm going to kind of use them to help you understand. But it's the increase in concentration of substances per unit of body tissue that occurs in successively higher trophic levels of a food chain or in a food web. So we have our little zooplankton in blue, and the zooplankton can have some kind of contaminant in them, and we'll call that contaminant PCB. And let's say that PCB is a compound that is fat soluble. So our zooplankton are going to absorb the PCB, and then a fish that has fat in it is going to eat the zooplankton that has PCB in it, and the fish is not going to metabolize that PCB. And every time the fish eats more and more of the zooplankton, it's going to accumulate more and more in higher concentrations of the PCB in his fatty tissue. And then we have a higher trophic level fish, let's call it some kind of bass, and the bass is going to eat this fish, and it's going to accumulate more and more and more and more of the PCB in its fatty tissue, and it will not metabolize it, it'll just accumulate more and more of it. Now, that accumulation, where it doesn't metabolize, can only be at this level, but as it moves to the next level, then that's what we call biomagnification, because now this fish here is eating a higher concentration with each dose, each taste. And by the time you get to the tertiary consumer, or the highest level, the apex predator right here, then every time the apex predator eats one fish, it's an incredibly high dosage of what was originally a small dose of the PCBs. Because it doesn't get metabolized, it concentrates more and more, and then at each trophic level, they're eating a higher concentration of it. Okay, so I'm not going to read all of this to you. I just explained how some of this works in more detail. So remember, biomagnification is the increase in concentration of the substance. I've borrowed a really nice picture for you to see the difference between bioaccumulation and biomagnification. So notice, bioaccumulation is where we increase in the concentration of whatever that contaminant is. We'll call it PCB in this case, persistent organic pollutant. Could be methyl mercury. And biomagnification is where we're moving from one trophic level to the next. And as we move through each trophic level, that concentration of what that predator is eating is also increased. Okay, mercury and PCBs are substances that bioaccumulate and have significant environmental effects. So we've talked about that. DDT, we know that it kills mosquitoes, but it's also a persistent organic pollutant that has done quite a bit of damage to eagles. Some effects that can occur in an ecosystem when a persistent substance is biomagnified in a food chain include eggshell thinning and developmental deformities in these top carnivores. So this is a top predator, and this is a really sad story about how the eagles were getting DDT into their diet, just eating fish that accumulated DDT and eating more fish that accumulated more and more DDT. And the eagles then accumulated it at higher concentrations, so that's biomagnification. And then it had a terrible impact on making their eggshells so thin that the eaglets couldn't even make it to birth most of the time. So then the eagle population decreased significantly. So that's an environmental effect. Okay, so I've reminded you about the consequences of biomagnification by talking about the eagle example. So remember that food chain piece, and then remember about our apex predators. Those are the guys at the top of the food chain. An example is a raptor like an eagle. And then remember the effects on humans. So learning disabilities, and then all those things that I had on that list. So humans do experience harmful effects also from biomagnification. And that includes the issues I just listed on the last slide, but also with the reproductive, nervous, and circulatory systems. So these are all the things that can happen from being exposed to any of those POPs and even methyl mercury from bioaccumulation and biomagnification. Short-term effects include memory loss, tremors, lack of coordination. Long-term effects include fatigue, weight loss, and even problems with the nervous system. I would pause this video and cover the answers at the bottom and just go ahead and give yourself a little challenge of this practice FRQ to see if you can explain everything that you just learned. And then uncover the answers and check and see how you did. If you still need a little more grappling with biomagnification, look up the Amoeba Sisters biomagnification video on YouTube. It's short and it's good. Well, that's it, guys. We're done. This is the end of topic 8.8. Go ahead and pause this. Make sure that you read, understand, and can describe each of the essential knowledge statements here. And this is Mrs. Gabriel signing out.